In this lecture, we're going to talk about JavaScript's object-oriented features. It's not like any language that you've seen before, likely. In Java, for example, I describe classes and use classes to instantiate objects. I also use classes to extend other classes and describe a type hierarchy. And then methods are found by looking through a sequence of classes defined via the extends relation. This is different from what happens in JavaScript, where I describe objects directly and then use prototypes to find methods using what's called delegation. This is a technique familiar from the language self, which is itself probably not familiar, but it's very similar to what's going to happen in languages like Java. These languages use a concept of vtable and a chain of vtables, very similar in some ways, conceptually at least, to the way that the prototype chain works in JavaScript. So what are these object literals? Well, it's simply some curly braces with stuff in between. If you don't write anything in between, you have the most abstract object you can get. It's an object with nothing in it. This corresponds roughly to a new instance of the object class. In Java, there are no properties of this object. If we want properties, we can list them between the curly braces. This is an object with 3 properties, name, age, and address. We can access those properties using a dot notation, and you can see here the person name is Alice, and the length of that name is 5. We can also update properties, so objects are by default mutable in JavaScript. Person.age can be incremented by 1. We can also look for properties that aren't there, and this is characteristic of a dynamic language. I don't know necessarily what properties are in the object in the compiler, and so we'll look for anything. What's the result I get? Well, it could be an exception, but that's not really consistent with JavaScript's goal to allow as much crappy code to run as possible. So JavaScript, again, is written with the assumption that programmers are not very good. Mozilla didn't want to break web pages just because there was some bad JavaScript. And so as a result, when you try to access a field that's not there, you don't get an exception, you simply get undefined. However, these kind of errors aren't deferred indefinitely. If you try to index into undefined, you'll get an exception. In this case, person.occupation results in undefined, then subsequently attempting to find the length of undefined gives me a type error with the error message, cannot read property length of undefined. And that makes sense because undefined doesn't have any properties. You can see this type of dynamism by writing a function that takes an object and then prints out various things about it. So here I'm going to take an object with one property called data, that is an array, and pass that into f. The code first prints out x, and what that will do is call the toString method on that object. This does not provide a new toString method, so it simply prints out the word object and declares its prototype. More about that later. Then I'm going to print out the data field, and of course we get out the array. And finally, we'll print out the length, and you can see that works no problems. What happens if I use an inappropriate argument, such as pizza? Well, pizza can be printed, no difficulties. The data field of pizza is undefined. And when I go to find the length of undefined, I get a type error. The same kind of thing happens with arrays. So here's a function which takes x and attempts to both divide it by 2 and access it as an array. So if I pass an array, the first expression gives me not a number. And so an array divided by 2 is not a number. If I invoke the function with an integer instead, the division works fine, but the attempted access into it as an array gives me undefined. Only if x itself is undefined will I get an actual exception on line 2. Note that undefined divided by 2 is simply not a number. You can think of an object like a map from strings to values. The strings are the property names, and the values are the property values. We can use the dot notation like person.name or person.age whenever the property name is free of spaces. We can also add new properties and iterate through them. So let's add a new property called occupation. Let's add another new property called happy place. Note that the second property has a space in it, and therefore I'm required to use this other notation in order to access it. Then I can iterate through all of the properties in this person using the for each loop and print out the property name and the value of indexing with that property. This is something that's not possible in a language like Java, iterating through all of the fields of an object. That's just not something we do. But it's perfectly sensible in JavaScript. JavaScript has lots of built-in functions to deal with objects, including json.stringify, which will print out any object in a readable form. So that's great. The objects I've shown you so far look something like hash tables, where we can actually add in new elements of the hash, and we can iterate through the keys of the table and get the values at each key. The power of JavaScript comes when we start using function properties. Here I've got a counter written having two properties, in and get. Get here is a function that returns this in and then increments it. Counter2 is just another way of writing the same thing. I have two properties, in and get is a function that returns in++. If I call the get function on both counters, I'll get 0 the first time and 1 the second time. In addition, I can simply access the get field itself, and what I get is a function named get. You can print out functions using toString, and what you'll see is the actual declaration syntax that was used to describe the function. So these two functions, even though they do exactly the same thing, they have a different toString because they're written differently. This is required in JavaScript. It's not optional like it is in Java. So counter1 will work properly here, but counter3 will not. The message I'll get is that in is not defined. And that's because I haven't used this, so I'm not referencing the in field of this object, and there's no global variable in that I might be referring to. JavaScript doesn't have private properties. So although this counter works as I expect, it has some features I may not want. For example, anybody who has a reference to this counter can update in to an arbitrary value, after which point the counter will proceed from there. So how do we achieve the effect of private state in an object? Well, in JavaScript, it's done using closures. So here's a counter factory that, when invoked, will return an object with a get method. Note that this get method accesses some local state. This is the local variable in of the counter factory. If I create a couple of counters using this counter factory, I can use one of them if I like. I can also invoke both of them, and you'll see that as I do that, I get the answers I expect. What's happening here is that createCounter is returning an object with one property, which is a function. That function doesn't access a second property of the object. Instead, it accesses a variable that was closed at the time that the object was created. This is in here is open when I create the counter and closed when I return. No one has access to this in object from outside the function. The function is closed around in. It's important to note that these closed variables are not fields. So if you attempt to use this on a closed variable, you'll get an error. It may not be the error you expect. In this case, what's happening is I'm trying to access the in property on this. This does not have an in property. Therefore, I'm getting undefined. And what's undefined plus 1? Not a number. You can see what's going on by trying to print out this.in and see that it is indeed undefined. Of course, a counter is just an object with one method, which allows me to increment. And so I could just represent that directly as a closure. Here's an encoding of that where I have create counter that has the closed variable in and then is returning this function. And now I've got a couple of functions C6 that you can invoke one at a time, two at a time, and they'll behave as you expect. JavaScript binds the special name this based on the calling context. You can see an article about it at Mozilla here. JavaScript has multiple contexts that can be used. These are the method context, a function context, constructor context. As an example, let's look at a really simple object that just has one property called getThis that simply returns this. You would expect that if I call o.getThis, I'll get back O. And fortunately, that's true. But what if I save the function getThis into a variable and then invoke that function? What do I get back? Well, unfortunately, I don't get back O because we're using a function context here, not a method context. And therefore, this isn't bound to the object or the target of the method call because there is no target here. The target was defined when I accessed the property, but it's lost at the point that I actually do the call. And it's the calling context that binds this in JavaScript. So what do I get here? Well, it's just some arbitrary nonsense. Brendan Eich, in a fever pitch in the middle of the night, decided that this should return the window. It just binds to the global context, whatever that happens to be. In a browser, that'll be a variable called window that corresponds to the window of the web browser. In Node.js, there's a corresponding global object which has access to the file systems and things like that. But it's kind of a nonsense meaning of this. It just means I don't know what this should be, so I'm just picking this arbitrary thing. This is one respect in which the treatment of functions in JavaScript really differs from the treatment in Scala. Here's a JavaScript counter, in this case doing a pre-increment and then returning this in. And as we just saw, if I save the next function into a variable and then invoke that, I'll get nonsense out. Well, what's going to happen here is that we're going to look for in the global context. Assuming that's not defined, I'll get undefined. And therefore, we're going to have undefined plus 1, which is not a number. Recall that in Scala, when I converted a method to a function, I had to use the underscore notation. What this does in Scala is creates a closure for this. Here we will bind this to the object, or Scala in this case. And therefore, when I invoke the function later, there's a meaningful value for this, and I get what I expect. So in JavaScript, methods really are functions. They're just properties that hold closures. This is not bound in the closure. It's just a free name, and therefore it has to be bound at the point that the closure is invoked. The closure is returned when you access the property. So if you save it somewhere else and then invoke it, you'll get the wrong value for this. Scala takes a different approach. Methods and functions are different, and this is why. In Scala, we close this when we convert the method to a function. This may seem like a technical point, but as it turns out, this causes a lot of trouble in JavaScript code. So here's a simple object with a value v and a function add that's going to take a list and add v to every element of that list. So we're going to return a new list here where every element of the old list has been increased by 5. That's what we expected to do. What does it actually do? Nana, 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 nana. This is not what I wanted. Why is this happening? Because this is inside of a function that's being passed around. The map code is invoking this function using a function context, not on the object O, and therefore this is meaningless. The standard fix for this in JavaScript is to save this into another variable that will actually get closed properly before you spawn off the helper function. And it does work, but it's not particularly beautiful. The attempted fix in ES5 is not very pretty. They gave us a bind operation, which allowed us to bind this to itself and close the variable this. It makes my head hurt just thinking about it. ES6 did a nicer thing. They gave us the fat arrow syntax, and fat arrows just deal with this properly. With fat arrow, this is treated just like any other name, and it is closed in the creating context, just like any other variable. As an example, consider the objects y and z here, which have a single property called getThese. GetThese is a function that takes a list and returns the result of mapping over that list with a function that simply returns this. So what would I expect if I execute getThese on 10, 20, 30? Well, I'd expect to get y 3 times. And indeed, that's what I do get. So if I look at the first element here and I say, well, what's the first element of the result? Is just y. That makes sense because getThese is mapping over the array, and for each element, it's simply returning this, which I expect to be y. What happens if I call z.getThese instead? I would expect the same thing, but note that here I've used the function notation instead of the fat arrow notation. And that means that this is not going to get closed. It needs to be closed by the calling context. And sadly, the calling context is wrong. So what I will get here when I attempt to show this for each element of the list is not z, but I'll get the global object, global or window, whatever it happens to be. Now let's turn to patterns of object creation and delegation. And to do this, I'm just going to look at a variant of the counter that we've seen. This is a function to create counters, which creates counters that are resettable. So here we'll start them off at -1, just for something different. We'll pre-increment. And when we reset, we'll reset back to -1. Here I can create a couple of counters, and they'll behave as I expect. So 1, 2. If I reset, the value or result of reset itself is undefined because it's executed entirely for its side effect. So here you'll note that undefined is used where we'd see unit in Scala. But then after the reset, if we keep going forward, we'll get 0, 1 as you expect. And of course, C1 and C2 have independent state in their independent fields in. In this case, I'm creating the counters using the function context. Note that the create counter function itself does not refer to this. This is only referenced inside of the closures that are associated with the properties of the object that is returned by create counter. Here we're creating an object using the object literal syntax to directly specify what it contains. Another formulation that's possible in JavaScript is to use a constructor. A constructor is simply a function that is invoked from the constructor context, that is, by preceding the function name with new. Any function invoked from the constructor context will have this bound to newly allocated memory. So here I can assign the in field of this newly allocated object to -1. I can update the next and reset properties as specified here. And now I have a couple of counters that in fact behave exactly as before. So this is just another formulation for how to construct an object using a function that's invoked through the constructor context. Why does JavaScript support these two different forms? Well, object literals are handy, they're nice and short, but they have some limitations, which are shared by the coding I have here. And in particular, note that each counter in this encoding has a separate closure for its next and reset. So if I create 1,000 counters, I will have 2,000 closures that I've created to hold these functions. The functions themselves are all identical. So why have all of these different closures hanging around? This problem is solved by using prototypes. The concept of prototype is a little bit convoluted, so let's walk through how they're used first, and then I'll walk through the implementation. To use prototypes, it's fairly straightforward. We have a function, that's the constructor function. We can specify properties for the objects that this function will create by making those properties of the function's prototype. And here I'm adding the next and reset function to the prototype instead of adding them directly to this object. If I do it, it's going to work just fine. So what happens here is the counters will behave exactly as I expect. What's happening is that there's another object created called counter.prototype, which has these two properties, next and reset. When I try to invoke the next function on C1, we note that C1 does not actually have a next function defined itself. And so the JavaScript engine looks into the prototype for C1, and it will go and find it that we've defined here. These prototype objects are similar to vtables, which we'll look at in C++. The prototype object is shared for all of the counters that are created using this function. Consistent with the very dynamic nature of JavaScript, it's actually possible to update the prototype object dynamically, and that will change the behavior of all of my counters linked through that prototype. So for example, I can use the counter as originally defined for a while, and then decide to update the prototype for the counter. And here I'm updating that so that instead of incrementing by 1, I increment by 2. And when you reset, I'll reset to -2 rather than -1. And now if I keep going along counting, note that I go from 1 to 3 to 5 to 7. Then when I reset, I'll go back to -2, which goes up to 0, 2, etc. This is something that has no analogy in Java or Scala. Here I'm sort of changing the plumbing behind an object. It's like changing the methods of a class while the program is running. This is something we just can't do in Java-like languages. So how is this implemented? Well, it's actually not that complicated, but it's unfamiliar, so it takes some getting used to. Each object in JavaScript has a special internal property called proto. And when we go to look up a method, like here I'm going to look up the next property of C1, you'll note that C1 itself doesn't have such a property. So what we do is we go to look at C1's prototype. That's actually found by looking at the proto chain, and we'll find the counter prototype. And there we'll find the next method. So what we're going to do is keep looking up this prototype chain until we find the definition of the property that we're looking for. There's some nice discussion on the internet, and you can click on these links. I'm going to just show you a few pretty pictures from those in a second. In the textbook, this idea of following a chain of prototypes is called delegation-based inheritance. But as you can guess, in JavaScript, it's called prototype-based inheritance. So prototype or delegate are synonyms in this particular context. As you noticed, I was using the word prototype when I defined a property on a prototype object, but I'm using the proto chain to find it. These are not the same thing. So every object has a proto field, but not every object has a prototype. Those are only for functions, and they're only meaningful when the function is called from a constructor context. When we invoke a function from a constructor context, the new object proto field is set to the function's prototype. So all of this is a little abstract. Let's just look at an example. Here I've got a function foo, And if you look in memory, you'll find the foo function represented as an object. And that function has a prototype because it's a function. It's pointing to the function prototype. The function prototype is itself an object, which is pointing to the Uber prototype, which is corresponding to the top class or the object class, which is object prototype. So this is ultimately where everything points. It's the terminal point in the directed acyclic graph of prototypes. And therefore, this object prototype has itself or nobody as a prototype. So we set the proto field to null. That's where every search stops. Note that whereas foo is a function, foo's prototype is merely an object. It is not a function, it's just an object. And so foo's prototype is pointing to the object prototype. We can then manipulate the foo prototype by adding x and calculate that, puts in an integer property and a function property. And then if I use the constructor context to invoke foo, creating a couple of objects, well, what's going to happen? I get two objects here, B and C. Each of these objects has its own Y field, but nothing else except the prototype, which is set to the prototype of the function that was used when I constructed this thing. And so therefore we get the proto object of B to be the foo prototype, and likewise for C. So now if I'm looking for the calculate property of B, I'll just simply follow the proto chain. We look first in B, we see it's not there, so we'll follow the proto chain until we find the function calculate. Of course, it wouldn't be JavaScript if we couldn't just change all this dynamically. So in addition to being able to add fields to proto objects, we can also change the proto object for an object directly. And so here I have an up counter and a down counter. I can create an up counter and count up for a while. Then I can switch its prototype to the down counter, and now it'll start counting down. So almost all of the links here can be changed dynamically. All right, so here we have this idea that B is an instance of foo, and that foo extends object. That's the way you can think about this in sort of analogy to a class-based language. Is it possible that foo could extend something other than just object? Well, you betcha. We can have an arbitrarily long sequence of prototypes between the object and the final object prototype, which ends the prototype chain. And here's a brief example. So I have 3 doggies here. They are Fifi, Shorty, and Woofy. And Fifi is a dog. So note that she is pointing her prototype to the dog prototype, which is different from the dog function itself. So here's the dog function, which creates dogs. This is the dog prototype object, and Fifi is one of these dogs. You can imagine more specific kinds of things, and we can imagine more general kinds of things. If we just follow the more general chain, Fifi is a dog, which is an animal, which is an object. There are several ways to set up such delegation chains from Fifi to dog to animal to object. One of them is to just directly update the proto field. So I can have a reset counter, which initially doesn't have any idea what next is. All it knows how to do is reset. But then I can take a counter and say to the reset counter, well, hey, reset counter, if you're looking for something that you don't have, go look in the counter. And after I do that, my reset counter will actually have a next method. The key line in this code is where I set reset counter prototype proto to be the counter prototype. And in the dog metaphor, what I'm doing here is setting the reset counter prototype proto field to be the counter prototype. So that's my introduction to the wonderful world of JavaScript object-oriented programming. You might be shocked at how dynamic everything in JavaScript is, and you might not be surprised that this can cause some performance hits. JavaScript had notoriously bad performance until Google introduced V8 for the Chrome browser and really revolutionized the world of JavaScript engines. How does it work? Well, the main thing that you have to do in order to get JavaScript to perform correctly is to get rid of all this dynamism. How can you do that without screwing up the semantics of the language? If you're curious, watch this 8-minute talk by Lars Bak from Google just to get a sense of what kind of issues come up.